Today, we're going to learn how to remove all the nodes from a binary tree using the clear function. Hello, I'm James Helfrich. When we delete elements from a binary tree, we must make sure to do it in the correct order. Otherwise, we may lose nodes and not be able to delete them. This video will demonstrate how to do that. To demonstrate how clear works, we'll start with an empty binary tree. When we call clear, nothing's going to happen. Now I'm going to allocate a single node, and when I say clear, it'll delete the single node. Now I'm going to allocate 3 nodes, and when I say clear, it will remove all 3 nodes. Now I'll allocate a collection of nodes. First, I'll call clear on P right, which will only delete the node Z, and then I'll call clear on P left, which will delete the node V, W, and X. To clear a binary tree, you must traverse the tree in a very specific order. I cannot delete the root node first because then I'll forget all about the left node and the right node. In fact, I must delete the root node last. Now, if there's no node, of course, I'm going to do nothing. And then I'm going to clear the left tree, and then the right tree, and then finally myself. And this is a left-right visit traversal. I could just as easily do a right-left clear, and that works exactly the same. To see how this works, consider the following binary tree. I'm going to start by calling clear on D. Now, I cannot actually delete D yet, because if I do, I will never have access to B and F and the subtree below it. So I will not be able to ever delete those items. So now I'm going to call clear on D, P left, which will be on B. And that's the same as calling clear on B. And then B immediately is going to call clear on A. Now A will try to clear P left, but there's nothing there. And then I'll try to clear P right, and there's nothing there. And then finally, I'll delete the node. Now I'm back up to B. Now B's left has already been deleted, so I'm going to call clear on B right, which is C. And C is going to attempt to clear the left, and it's going to attempt to clear the right. Neither of them exist, and then I'll delete myself. And now back up to B. So B's left has been deleted, and its right's been deleted, so now it can delete itself. So now we're going back up to D. Now D's left has been deleted, and now I'm going to call clear on P right, which is F. Now when I'm in F, I'm going to attempt to call clear on P left, which is E. Now E is going to attempt to call clear on P left, which doesn't exist, and right, which doesn't exist, and now I could delete my node. Now that returns control back up to F. F's P left has already been cleared, so now I'm going to attempt to call clear on P right, which is H. Now I'm at H. H will attempt to call clear on P left, which is G. G will attempt to call clear on P left, which is a null, and then right, which is a null. And then since both those are empty, then I can delete myself. Now return control back up to H, which left has already been done, so I'll do right, which is I. I has no children, so I'll delete left and right. And now we're back to H. H is left and right's been deleted, so I can delete it. Now I'll get back to F. F's left and right has been deleted. I'll delete it. And that leaves us finally with D. Since D's P left and P right is deleted, I will delete it. Notice how the root is always the last node to be deleted when you're clearing a binary tree. We can learn more about this by reading the binary tree chapter of the C++ data structures textbook.